Welcome to episode 38 of the What's Up podcast, recorded by Auld Reekie Astro. Today's the 27th of June 2019. My name's Martin.
I'm Ali.
And I'm William.
So today we're going to discuss a few stories that have caught our eye, all based around our sort of back gardens we're going to refer to. In this case, though, our garden's going to stretch out quite far into the solar system. So we've got three topics to talk about. Let's start off with Ali. What do you want to talk about today?
I want to talk about Uranus. Excellent.
That's out the way.
You've got to acknowledge that moment just once. But there was a recent story that just popped up just last week, actually, about somebody's taken a new observation of Uranus's ring systems. And for those of you that aren't aware, Uranus is the second outermost gas giant, and it's technically an icy giant because Uranus and Neptune together are made of more ices than are Jupiter and Saturn. So they're technically in a different class. They're about 4 times wider than the Earth. And Uranus is weird. And
that's a bit harsh.
Well, there's lots of weirdness about it. So it's always interesting when somebody does something new. But they've pointed ALMA, so the submillimeter instrument in Chile, they've pointed it at Uranus to study its ring system for the first time. So this is actual thermal emission from the ring particles. And everyone's familiar with Saturn's rings, and they're quite well understood because we've had Cassini doing a very good job of imaging that from multiple angles. And it turns out Uranus's rings are also weird. And particularly the brightest of these rings, and it turns out that it's a little bit warmer than they were expecting, and they've got evidence that there's not a single bit of dust in the rings, or a tiny amount of dust, because of the observations that they've got. And that's a little bit weird because just about all the other ring systems that we know of have very dusty small particles all the way up to, bigger boulders and maybe even house-sized things in the case of Saturn's rings. But Uranus's ones seem to be centimetre-sized and up for this particular ring, which is interesting because it's another thing to solve. Why does it not have any dust? So it's quite a wee story, but I thought it was interesting because Uranus is full of things that we still don't understand.
Well, it's kift, isn't it?
Well, it's
technical term.
What do you mean?
It's on its side.
It's rolling about on its side, kind of like it rolls like a barrel, whereas a lot of other things are rotating with the equator of the planet pointing towards the sun.
So
everything else is.
So rather than like our planet's rotation axis being quite well aligned so that it goes kind of in the same way as it goes around the sun, we're saying that Uranus is leaning over on its side.
Yeah,
so
kift.
Going at a strange angle. So yes, kift is you're going to say.
So I think it doesn't sound silly that effectively it means one side has continual daylight. Well, who doesn't?
Would you like some stats about Uranus? 42 years.
42 years to precise.
Pole. Yeah, so 42 years in sunlight and then 42 years of darkness if you're on one of the poles.
Darkness.
It's quite a cool stat. It's also the coldest place in the solar system that we've measured with probes. So
I'm going to call you out on that one because that's actually not true. The coldest place in the solar system we've ever seen is on Earth.
Really?
Because in labs we've created spaces that are far colder than anything else.
You are splitting hairs.
Similarly, the hottest place that we've ever measured in the universe is inside the Large Hadron Collider during a collision.
So what do you think? I may have to give you that.
Coldest naturally occurring place that we've spotted.
Can I just call it the second coldest?
That's fine.
Which incidentally might be the coldest place in the universe, not just the solar system. Because unless there's another intelligent species who are doing a similar thing, which I mean there might be, but it's arguably the coldest place in the whole damn universe. Pretty exciting.
I'm a little bit nervous. I have opened a can of worms here.
Sorry, it's a little bit off topic, but it's
interesting because it's cold. It shouldn't be the coldest. Neptune's further out. Neptune should be colder. They're both icy giants. Why does Uranus have less internal heat coming out of it?
Smaller?
They can't find. There's hardly any extra heat coming from the inside. So even the Earth radiates more spare heat than Uranus does. And it basically radiates all the sunlight that falls onto it straight back into space, but there's no hint that there's extra heat coming from the internals of the planet, whereas every other planet that we can measure this for, you do see a little excess, maybe from decay or heat in the core or radioactive elements, but there's a little bit of something, and for some reason we don't see that at Uranus. And that might be to do with the fact that it's been knocked on its side.
Yeah, so the knocked on its side thing, I mean, could that be linked with why this ring structure seems different to other ring structures? I mean,
I guess the short answer is yeah.
I mean, like Saturn, we think that the ring is from a disrupted moon or something like that.
Yeah, and so you need to figure out why there's no dusty bits. So is it fresher than some of the other ring particles? They haven't had a chance to collide and smack into each other enough, or is it arguably older, or something else has come through and cleared the dust away, or all the dust is congealed onto the bigger bits? So it's lots of interesting stuff.
And so it's worth saying this was seen with ALMA, which, as you say, is a sub-millimeter telescope. So it's looking at things which are wavelengths of light a little bit shorter than a radio telescope.
Yeah, cold stuff.
And this measures dust generally, doesn't it? Or small cool particles.
Yeah, well, they're comparing it with infrared observations with VLT, and the comparison allows them to go, there's hardly any dust, because they're getting the same sort of color ratios from the sub-millimeter as they are from the infrared, and you would expect the infrared to be squelched if there was a lot of dust there. Because the sub-millimeter should pass through all that, but because you're seeing sort of the same thing, it means there's hardly any dust interfering with that extra light. So it's just another one of these things where you can't... This is the problem with Uranus. There's not much data on it. We've only had one probe, and everything else you've got to do Earth-based. And what's quite nice is once Webb telescope is up and running, it's probably going to have some science to do pointing at the gas giants, and that includes the icy ones. So we will have slightly better data this time in the mid-infrared, and maybe some of these answers will get solved. I think the best theory for why it's weird is that it's been smacked into at some point in the past by something bigger than Earth. And that's one of the reasons why it's strange. And you can see that in some models, but I think the jury's still out on exactly what's going on.
Yeah, and getting there is quite tricky.
A little bit.
Actually, as a possible kind of teaser to what we're about to talk about, the orbital dynamics of it are kind of intriguing, because we've only been there once, as you say, which was Voyager 2.
Did the grand tour, which you can't do for at least another 60 years or something.
Flukily aligned
everything
planets.
Was lined up,
where it just went whizzing by, but part of the, and it's worth highlighting as well, that's 40 years ago, 30-something years ago now, so I'm sure it was a phenomenal spacecraft. It is a phenomenal spacecraft, but the detectors and equipment which was there is not quite the same as the sort of things we're now getting, those high-definition images coming back with Juno. But the other thing is that because of the orbital dynamics, it's really hard to put something in orbit around Uranus, isn't it? I think that you've got to get up so much speed to get there in a sensible amount of time that you probably need some fuel to brake and slow down to get yourself into orbit. But if you've got to take fuel, then you're more massive, and it becomes a real nightmare, which I think one of the reasons why it hasn't been done. But I saw a paper discussing it, trying to talk about crazy missions where you could do it, but it was going to be a really difficult thing.
It's the same reason why New Horizons didn't do a orbit of Pluto. It was going so fast to get there in reasonable time. You have to swing past. You can't stop and slow down.
It's almost like the first question you have to ask: to fly by or not to fly by? That is the question. Far away things, I think you're better off with flybys.
And I think that leads us really nicely into a different story. So, William, what story is this?
Indeed, yes, it does lead us nicely to the interview which we recorded earlier with a very important person who works on the site here at the ROE with us. So we are lucky to be joined by Colin Snodgrass today, who is the deputy lead of the Comet Interceptor mission, which has just been accepted by ESA. I think I'm saying that right, and hopefully you're nodding, which is a good sign. What's it all about?
So this is it's fairly well. It does what it says on the tin. So Comet Interceptor is to go and fly past a new comet. So the way that you can go and visit a new comet coming into the solar system for the first time is to go and build a spacecraft that will loiter in space and wait for it.
Loiter in space, yeah,
yes.
That's good. I like that.
Because the problem is with these comets is when they're coming in, normally we only discover them sort of months to years in advance, and it takes a decade or so to plan and build a spacecraft. So to try and meet a new one coming in, you've got to build the spacecraft before you know the target, launch it into space, and then wait for the target to come to you. So this is what this mission does, which is kind of different from anything we've tried before.
So what are the kind of time frames you have to wait? I mean, how long does this thing loiter? Where does it loiter for starters, I suppose?
So it's meant to launch in 2028, and it launches with the Ariel Space Telescope, which is a ESA telescope to look at exoplanet atmospheres. And that's going to go to the Sun-Earth L2 point, so the Lagrangian point, which is where the gravity of the Sun and Earth balance out, and you can park in space with very little fuel used.
This is the same place as JWST.
Yeah, it's where JWST is going. It's where Ariel's going.
It's a busy patch of space.
A gravitational sweet spot.
Exactly. So it's a good place to park in space. So that's why you put telescopes there. That's where Herschel Space Telescope was. So you can put a whole bunch of things there. And one of the things we're going to put there is Comet Interceptor, which is going to just kind of, hang out there, try not to crash into JWST and Ariel and all the other things that are loitering out there. And then it can wait there for a few years, basically. So the main driver on how long you can wait is building your spacecraft to survive in space for not too long. So it'll be designed to be operating for about 5 years. So that's a few years waiting, a couple of years after leaving L2 cruising to intercept the comet, and then a couple of days of actual science as we go flying past the comet really fast.
So it's 9 years of planning, 5 years of loitering, 2 years of travelling for a couple of weeks.
A couple of days of encountering a comet in which all of the juiciest data is a couple of hours right around the closest approach, because it's a really fast encounter. Because this is one of the things, if you're going to a comet that's coming in from the Oort cloud, or coming in from potentially even from outside the solar system, these things are going really fast relative to you. So this thing's going to be tens of kilometers a second, up to maybe sort of 80 kilometers a second in the worst case, if it's some retrograde comet that's orbiting the sun the opposite way around to we are, because then you just meet them really, really fast.
Yes.
Does sound quite dramatic. Can I just check, because this is quite timely that we have you here. So are you even still hungover from the official announcement? Because we should probably explain how all this works. I mean,
yeah. So we only got told this last week, on Wednesday last week. So it's a week now that we known about this thing, and yeah. So already, a couple of days of frantically emailing everyone and going and talking to various press things and so on, and then we were already started. So I'm back today in Edinburgh from yesterday. I was at ESA's headquarters in ESTEC in the Netherlands, where we already started the design process. So I spent yesterday talking with ESA engineers about how we're actually going to make this thing work, and because they kind of take our proposed plans and then tear them up and start again from scratch and say, okay, that's how we're really going to do this. And so there's an ongoing process at ESA at the moment to kind of redesign this whole thing from basically here's the science requirements and the instruments we need, let's make this work.
I like it. So the minute the green light comes in, you're like, right, it's time to get to work.
Go. Yeah. So I mean, this is the first F-class mission from ESA, which is fast class, and they we were all sort of joking, okay, fast for ESA, it's okay, it's only 9 years, but I mean, they really mean it. They were well done, you have a mission, and now go and book some flights.
They'll always be looking at you from the corner of the room, tapping their watches and going,
Yeah, exactly. It's like, what do you mean you still haven't figured this bit out yet? On you go. So so it's it's going to be exciting.
I mean, it is a quick turnaround, isn't it? Really, 9 years for planning and getting ready a space mission. Is that actually? Yeah, it sounds a long time, but it's by space standards, it's really not.
It's really not, especially because the way that ESA does these things is so we kind of designed this whole mission and wrote a proposal based on some this is how it should work, and had to write this in a convincing enough way that it looked like it would work, and we had some support from kind of space industry companies who build spacecraft and said, this will work.
Can I ask how long ago, when did that process start, and were you there from day one kind of thing?
Yeah, so in this case, it's also only been a year or so since they actually put out the call for this and announced that was this opportunity. So I mean, it's
10 years from back of envelope to actual mission
Yes,
launch.
Exactly. So there's, we had about this time last year, a call went out with first deadline for outline proposals would have been kind of late summer last year. By Christmas time, they'd kind of whittled that down to 6 proposals that they thought, okay, this sounds interesting. And and asked each of those teams to prepare a more detailed proposal. So that's when you went and, you spoke to someone who knew about actually building spacecraft, and you kind of wrote a 40-page or 50-page detailed proposal. And then from that one, they've now selected one. And now we go into a sort of initial design study with ESA and their engineers for the rest of this year or so. Next year, they'll kick off another detailed study with space industry, who'll spend a couple of years designing alternative versions, and then finally they'll pick the version they like.
Okay. I'm sensing this is a silly question, but I have to ask it. Do they have any pomp or circumstance when they award a mission? Is there like a moment where they give you a red rose?
There was a panel meeting of one of the sort of senior committees in ESA last week who were deciding on this, and essentially we got an email going, well done, it's yours, about the same time as they announced that to the world, and they put it on this nice article on the website. It's like, by the way, you've got this. And then it's like, oh, good. And then, immediately you start tweeting like crazy, and,
I saw some of those, yes.
Yes.
It's nice that we've got you here. Who's your partner in crime, by the way? Sorry that I've forgotten who you're...
It's Geraint Jones at MSSL, which is part of UCL in London, who's the lead proposer, and me. And then there's a team of people from all over the world, actually, because we've got this whole European team that's leading it, but then this mission is also joint with the Japanese Space Agency, JAXA, so there's a large group there. And there's some folk in the States as well. We're working through NASA to contribute one of the instruments, so it's quite a kind of international plan.
So the fact that it's kind of a fast mission, does it mean you can be more risky than other missions might be?
In some ways. I mean, overall we can't, but one of the things that we're doing with this particular mission is, so we have the spacecraft that waits around at L2 and then goes and flies past a comet. Just before it gets to the comet, it will release a couple of smaller probes or sub-spacecraft. And so the main spacecraft will have a reasonably safe distant flyby of the comet, about 1,000 kilometers or so from the nucleus. So still well within the coma and the gas and the dust of a comet, but not in the most kind of dense part where there's most danger. But it will release these couple of probes that will go a bunch closer. They can take more risk. So they are designed to, they should survive, but it's not mission critical that they do. So they're transmitting data back to the main spacecraft kind of all the way in. And
right.
If they don't make it out the other side, then the mission still succeeds.
Yes.
And are you aiming to ultimately orbit the comet, or do you only have a flyby chance?
It's just a real fast flyby.
Okay,
so there's no way we can match speeds in orbit like we did with Rosetta.
Because you don't have the time to...
We don't have the time, and mostly we don't have the fuel to do this. So with Rosetta, which is a short period comet, it takes 6 years to go around the sun. The spacecraft could spend 10 years kind of orbiting, doing flypasts of a couple of planets and building up speed to match the orbit. Whereas for a long period comet like this that's coming in at high speed, there's just no way we could do that.
So how do you choose, right? Say you get one that's got a non-optimal trajectory and you're kind of like right on the margin of whether or not we can do this. Who's the person whose weight that will be on for the yes or no, thumbs up, thumbs down for lighting the candle?
So there'll be a few of us that are making these decisions. We probably won't leave it to one person. I mean, so the ESA, so there'll be an ESA engineer team who will say whether or not they think it works as possible, and they probably won't let us do anything too crazy because they tend to be more responsible people than scientists. And then there'll be a science team kind of going, oh, that looks like an exciting one, or this one. So in an ideal case, you've got 2 or 3 comets potentially to choose from in the period you're waiting.
Do you also have to list, all the various things that you want to see happen for criteria that you're looking for? So this kind of speed and this kind of trajectory.
Yeah, I mean, I think that largely we'll pick the one that works, and as soon as we find one that we know works, we'll probably go for it. But I mean, there's probably a long period between discovering it and kind of before you actually have to fire the rockets and go. So you can kind of keep an eye out for does something better come up in the meantime. But
are you allowed to jab other telescopes in the ribs for some help to help classify.
I imagine we might be doing that a bit,
so that
we kind of one of the nice things about this, the timescale of it, is that we will have the LSST survey coming online next couple of years, and this is going to find so many more things of every type. So it should, it almost certainly it will be the thing that discovers our comet, and then it will keep going its survey. We'll get quite a lot of data from it anyway, just from on the ongoing survey. But probably will also be then writing proposals for everything else to say, okay, we want to characterize this. We want to go and look at it with JWST before it comes in, and we want to go and
It's very exciting.
So you mentioned something about an interstellar thing, so Oumuamua type objects which came from another system. Is that a possibility?
It's a possibility. Yeah, in terms of intercepting something, there's not that much difference between an interstellar object and an Oort cloud object in terms of sort of speed it'll be coming and so on. The big difference is likely to be two main differences. Firstly, there are going to be more Oort cloud comets coming in. We think there's a much higher probability we'll get one of those within the time frame that we can reach. But the other thing is if all interstellar objects behave like Oumuamua, then they don't have this big coma, they don't have this activity, they don't have the tails of a comet. So you don't spot them as far out.
Okay, yeah.
So for the same size of object, you can see a comet coming much further away than you can see something that behaves like an asteroid, just because it has a much bigger reflecting area. You've got all of the coma. So we'll have many years warning with LSST of an incoming Oort cloud comet, and that's time to fix the orbit, take these observations to characterize it, be sure that's the target you want, calculate and recalculate the trajectory, and be sure of all the numbers and go, yes, definitely that one, make a decision. Whereas if it's something like Oumuamua that we have only weeks, it's really having to phone up someone at ESA in the dead of night and go, hey, go, fire the rockets. And that will make ESA more nervous.
Yes. So. Will you have to sneak up in sort of automated fashion where the probe itself is doing that's where it is and sort of refining things given the distances?
So on approach we'll be able to use the cameras on board to sort of see the comet and refine the trajectory a bit in the kind of months and weeks leading up to it, but at the very fast bit, the very end for the flyby, it'll have to kind of autonomously track the comet as it swings by, just because everything happens so fast. There's no way to command that from Earth.
I think, was it one of your tweets where you suggested, can we have some more shiny cartoons from ESA, please?
Yes.
For those of you that aren't aware, the Rosetta mission had some really pretty cartoons where they sort of anthropomorphized the lander and the orbiter, and I would love to see more of those. So I would hope that would be true.
Yes. Well, we already spoke to the people responsible for the Rosetta cartoons. They are also very keen on doing more Comet cartoons. So hopefully that will happen.
Very cool. Does the name change at any point now? Are we to call it Comet Interceptor for the time being?
It's Comet Interceptor for now. We may at some point rename it or potentially name the individual 3 different spacecraft that make up Comet Interceptor. They might give them names at some point, but we haven't done that yet.
It's a good name because it's a name which tells you what it is, as you say. It's like so often the names are completely random and disconnected. So it's nice.
But in the same token, if you can get to command the Snodgrass Comet Interceptor,
that's
I'd be pushing for that one.
I suspect that Graham might have some words to say about that. But
very cool. Well, thank you very much, Colin. That's awesome to hear about, and hopefully find out more as the design sort of crystallizes, and it'd be good to talk again.
Yep. Well, it's a long process from here, so many chances to talk again about this as we go ahead.
Yeah. Good luck.
Cheers.
All right. Thanks.
Thanks again to Colin for joining us for that interview. I'm sure something we'll hear a lot more about in the press, as well as something we'll have a chat with him over lunch on a regular basis. All the trials and tribulations of a fast-track satellite mission. It's going to be a real challenge. Okay, and I think we've got one more story I just wanted to quickly highlight. This is one that I spotted in the news, which got a fair bit of press, column inches, I suppose, which was that Curiosity, the Mars rover, has detected a methane spike, and what the implications of this might be. And a bit like the Uranus story, getting lots of press coverage for something that I don't think is that necessarily a lot to say about it. I fear this is a little bit the same thing.
Well, it is interesting and bizarre. It's just the fact that it's got a very tenuous link to life.
Yeah, I think this
means
is what
it gets
dun.
Yeah, this is Curiosity has detected a spike of methane gas. So a big plume by the standards of plumes of methane that is detected previously on Mars. So quite a big one. It's like 18 parts per million. Now the Earth's atmospheric concentration of methane is about 1,800 parts per million of methane. So okay, firstly, just adjust that parameter. So we're not saying it's discovered a swamp full of bacteria on Mars. That's not the case, but it has detected a weird spike. And also, this could just be something else. It could be a geological process. It could be old. It could be new. It could be lots of things that have happened that's released this pocket of CO2 of methane. But it might not be a bacteria fart.
How do you ever convince yourself it's one thing or the other? Is that, this isn't the first plume Curiosity's seen, I don't think.
No, I think it's just the largest.
It's the largest,
yeah.
Okay. So at some point, if you see enough large ones, does that convince you that it's not geological? But
no, I don't.
Or you might never be able to answer it completely.
No, but I think the thing that's really intriguing, I don't think was expected, is that it hints at a very dynamic system in that, because I seem to remember there were early measurements which were taken from an orbiter which hinted at higher levels of methane, and then Curiosity's first measurements went no, not that high, and then actually suddenly you get a plume and it seems to vary, it seems to be changing, which suggests that whatever is there is it is being generated recently. I think it would be I think they expect it would be more evenly distributed throughout the atmosphere, and you wouldn't get these kind of bursts if it was an old reservoir. So that in itself is kind of intriguing, because it means that, and it's actually fits in with lots of other things we found out through Curiosity and through all these many missions. It's so funny, we were saying about Uranus that we've had one thing there which flew past pretty damn quickly. There's loads of stuff looking at Mars, and one of the stories
we're spoiled.
We
Mars,
are.
Yeah.
One of the stories which keeps coming back more and more is that this is a very active, dynamic place. It's got we know it has seasonal variations, but it also has it's got seismic activity. It's got possibly sort of water, very high salinity water, which is sometimes
there's something rolling down the slopes for sure.
Yeah,
and I'm a huge fan of the Dust Devil videos that I think
phenomenal.
Opportunity and Spirit had, and they're really pretty. And they're incredibly tenuous, but they're physical things that you can watch roll across the landscape and leave marks in the dust. I mean, it's changing all the time.
In comparison to the moon, which, I mean, obviously, a simple comparison, but something like that, which is a very dead world. There's very little happening. I mean, it's got no atmosphere, but it's just such, it doesn't change much. Whereas this thing is a really lively, different, sort of not ecosystem, definitely not necessarily an ecosystem, but a different environment and climate. So this just fits into that pattern, which is really cool. And there's another interesting riddle to try and solve. We need more craft. We need to go again.
So the last time I heard about methane on Mars, they were saying it might be seasonal. There's a tentative.
So there is a seasonal variance.
Is it fitting in with that pattern?
No, this is a plume that sits outside of that pattern. So there's like kind of a broad yearly cycle of seasons, but this is like a proper pump.
Nothing like an outlier
Something's triggered it. Yeah. Which is, I think you can distinguish between geological processes that create methane and biological processes that produce methane by other gases and details, but Curiosity doesn't have a full lab on board, doesn't have all the possible equipment you can ever want. So with the instrument it's got, I don't know if it can distinguish between them.
That's a good question, because the ExoMars rover that's coming, that's going to be quite exciting. Does it have a methane sniffer? I'm imagining it probably would, because it's going a little bit further where Curiosity can't quite just yet. So
what about Insight? Has that monitoring as well for methane? I think it's quite possible.
It's got the equivalent of a cup to the ground, so I don't know if it's got time to sniff for methane at the same time. You never know.
But even then, if this is a dynamic process, are you going to be able to, with either of those things, find the thing that caused this? So it's just a really fascinating thing, and loads of questions coming out of it. And I guess these are questions we will come back around to in future episodes, so I guess that's a good place to leave it. Thanks very much for listening.
Cheers all.
Bye.